So a nice easy one to start with. A 200 picofarad capacitor is discharged through a 2 megohm resistor. Calculate the time constant. What's the formula for time constant?
T equals to RC.
T equals RC. So what do we do?
Resistance is 2 mega, so it's 2 into 10 to the power 6.
Okay, now be very careful, that's the point. Please, in an exam situation, be very careful with your units. You've got a 2 megohm resistor, so you don't just put 2 in there. That is 2 times 10 to the 6. And the capacitance is 200 picofarads.
10 to the power minus 12.
Pico 10 to the minus 12, that's good. So 200 times 10 to the minus 12, which is 10 to the minus 2 times 10 to the minus 10. So the time constant is going to be 4 times 10 to the minus 4, which is 40 milliseconds. Okay, now in terms of pico, remember with the capacitance, we often quote capacitance in microfarads, nanofarads, and picofarads. Microfarad 10 to the minus 6, nanofarad 10 to the minus 9, picofarad 10 to the minus 12. So these are very small, isn't it? Picofarad 10 to the minus 12, it seems incredibly small. It's all based on the fact that a farad capacitor is enormous. And at high frequencies, even this sort of capacitance can be quite significant. What is meant by the time constant of a circuit? Can anybody tell me? Time constant of a circuit.
The time it takes to do the charge distribution.
To what level?
To half of the
Half?
previous level, like
No.
it's exponential.
It's exponential. Let's take that kind of formula you know about. Q equals Q naught. You should know this formula. Q equals Q naught e to the minus t over RC. Here's a time constant coming in here. Now we've said the time constant is RC. So if we put RC in for t, then this power is 1. So we get Q equals Q naught e to the minus 1, or Q naught divided by E. So it's the time not to fall by a half, but to fall by a factor of E, which is around that 0.37 of its full value. That's one way of looking at it, but there's another way of looking at it as well. Take this formula here and take logs of both sides, natural logs. So ln of Q equals ln of Q naught e to the minus t over RC. Now you can split that product up, so that equals ln of Q naught, sorry, plus ln of e to the minus t over RC. Now pull that power out, so we get ln of Q naught plus minus t over RC, ln of e, and what's the ln of e?
1.
ln of e is 1. The natural log of e is 1. So we get, to cut a long story short, I'll put it over here, camera can get it any better, ln of q equals minus t over RC, I'm just swapping the order, plus ln of q naught. Now if we compare that, if we do, well let's do a graph first of all. If we do a graph of ln of q against t, what are we going to get?
Straight line with a y-intercept on Q.
Good. We're going to get a straight line with a y-intercept there of ln of q naught. If you're puzzled about that, just compare that to y equals mx plus c. Here's the c, and here's the gradient. So the gradient of that line is going to be the time constant of the circuit. All right. So that experimentally, if you were doing this as an experiment and you were making lots of measurements, So you had a capacitor and you were discharging it through a resistor. We know we get this sort of curve. But if it's an experiment, then you'd expect the points not to lie perfectly on the curve, etc. So the way you would normally do that is take your data, take the log of Q and plot it against T, and then you get a straight line through your data points. And the gradient is RC. Did you get that? All right? Okay. Because I could ask you to do that sort of thing in the exam.
Is it RC or is it one?
I'm not doing all these in order, so I'm going to go on to, yeah, this one, number 6. We have a container with some sort of heating element in it, and it's got a liquid, and a current of 5 amps passes through the element, and it has a resistance of 40 ohms. We have 2 kilograms of water, and the temperature goes from 30 to 70 degrees centigrade. And I also give you that the specific heat capacity of water is 4,200 joules per kilogram per degree centigrade. And we're wanting the time needed to heat the water from 30 degrees to 70 degrees, assuming no heat loss. How would you go about this? Any thoughts? This is bringing in a little bit of the material you'd have done in Physics 1. Can we calculate the heat supplied, or the energy supplied, to the water? How do we calculate the energy supplied by the heating element to the water?
Well, the weight times by
The electrical energy is
energy.
power. What do we know about power? Power. Formula for power.
Energy transfer by time.
Yeah, okay, but let's just do, we know that power equals VI, and we know that V equals IR, so we can plug that in to eliminate V, so it's I squared R. So that's the power supplied. Now the energy is the power times the time. So let's call that time T. So that's time, not temperature. No, sorry, that doesn't equal. Get rid of that. Undo. So the energy E equals I squared R times the time. Okay, so that's the energy supplied. Now, if there are no heat losses, all that energy goes into the water and nothing goes out. So we need a formula, an equation for heating water. How does the energy we supply to water or liquid or something when we heat it relate to the temperature? I'm sure you must have done this last year. Any ideas? Come on, you're in an exam. If you fail this question, you fail the exam. It's the one question that's going to get you through the exam. Any ideas? Heat supply, we'll call this Q as well while we're at it. The heat supplied is the mass of the material, the specific heat capacity of the material, which is 4,200 joules per kilogram per degree centigrade. And then θ2 and θ1 are the temperatures, so we're going heating the water. So we know the temperature rise, don't we? The temperature rise is 70 minus 30. So we've got 40 there. We know the wet mass is 2 kilograms, so Q equals 2 times 4,200 times 40. That's the energy that we've had to put into the water to heat it, and all that energy has come out of the heating coil up here. So all that energy is supplied by that. So we know I, do we know? Yes, we know I. I is 5, so I squared is 25 times 40 times the temperature. 25 times 40, 425 is 100, 1,000, so 1,000 T. So 1,000 T equals 4,200 times 80. If I would cross those off with those. I've got 42 times 8 as our answer. If I didn't make a mistake, 336 seconds.